Hello everyone, I will be presenting our paper which is titled A Deflation Based Fast and Robust Preconditioner for Bundle Adjustment. This work was done in C-Star Lab IIIT Hyderabad, India. Recent advances in structure for motion has moved towards problems involving millions of images. One of the bottlenecks in this assessment system is the bundle adjustment process, which involves the minimization of a non-convex cost function. We can understand the bundle adjustment process from this example. Suppose we have three cameras C1, C2 and C3 and 3 points x1, x2 and x3. The observed projections of these points are given by the m's and the computed projections are given by the measurement function ri. The measurement function takes into account the 3D point parameters as well as the camera parameters. The difference between the observed projections and the computed projection is the reprojection error. The bundle adjustment process tries to find optimal 3D and camera parameters such that the total reprojection error is minimized. Now we look at the problem formulation for bundle adjustment. As discussed above, the difference between the observed projection in camera K, say nk, and the computed projection Rk of x of a certain 3D point x is the reprojection error denoted by Fk of x. If we stack the reprojection error for all the cameras, we get this function f of x. The bundle adjustment process tries to minimize the norm of this function by finding an optimal vector x. The objective function we saw above is a nonlinear function. It is usually minimized by the Levenberg-Markov algorithm, which is a nonlinear least squares solver. In each step of the LM algorithm, we need to solve a linear system which is of the form as shown here. The matrix HLM is the Hessian related to the bundle adjustment problem. Now we define the condition number for matrix. The condition number for matrix is defined as the ratio of the largest eigenvalue of A to its smallest eigenvalue. In our paper, we use GMRES for solving the linear system, which is an iterative method. For iterative methods, the rate of convergence depends on the condition number of the coefficient matrix. In fact, high condition number slows down convergence. For bundle adjustment problems, HLM is the coefficient matrix. It has been observed that bundle adjustment problems are very ill conditioned. Iterative methods for badly conditioned problems require a preconditioner for speeding up the convergence. Hence, recent research has focused on designing efficient preconditioners. In this paper, we design a preconditioner using deflation. Deflation involves removing or deflating the unfavorable eigenvalues of the coefficient matrix. Our approach is motivated by the fact that a few of the largest eigenvalues contribute to the very high condition numbers associated with bundle adjustment problems. Deflation is generally done for removing the smallest eigenvalues. However, we deflate the largest eigenvalues because computing the largest eigenvalues is cheaper than computing the smallest eigenvalues. In our previous paper, we designed a preconditioner using the two-grid method. It consists of the multiplicative combination of two components, a coarse-grid correction which is constructed by deflating some of the largest eigenvalues and a Jacobi smoother. The reason for using a smoother is that the coarse-grid correction is low-ranked and thus cannot be used as a standalone preconditioner. The smoother helps to maintain non-singularity. The preconditioner we discuss in this paper is given as shown here. One of its advantages over a two-grid preconditioner is that it can be used as a standalone preconditioner. Here the columns of P contain the eigenvectors of A corresponding to K largest eigenvalues. The algorithm for solving a system with BD as a preconditioner is shown here. It should be noted that the preconditioner matrix BDA is non-symmetric. Thus, we use GMRES as an iterative solver. Now, if lambda 1, lambda 2 up to lambda n are the eigenvalues of A, such that lambda n is the largest and lambda 1 is the smallest, then the effective condition number is lambda n by lambda A. However, when we apply BD as a preconditioner, the effective condition number reduces to lambda of n minus k by lambda 1. These are the details of the dataset that we use in our experiments. It can be seen that the size of the Hessian ranges from 200 k to 2.9 million. Here are the implementation details for our experiments. For our experiments, we deflate the two largest eigenvectors. In this plot, the 10 largest eigenvalues for the Hessian or the Venice problem is shown. It can be seen that the two largest eigenvalues are much larger than the rest. Thus, deflating the two largest eigenvalues leads to a considerable reduction of the condition number, which in turn leads to faster convergence. Here we plot the time taken for computing the two largest and two smallest eigenvalues of the Hessian for the given problems. It can be seen that computing the smallest eigenvalue is almost 1000 times slower than computing the largest eigenvalues. Thus, we deflate the eigenvectors corresponding to the largest eigenvalues. The proposed solver was integrated with the series solver, which contains many state-of-the-art solvers already implemented. We compared the time taken for 100 iterations of the LM using the proposed solver with the solvers implemented in series, as well as a modified version of the two-grid solver. It can be seen that the time taken for our solver is much less compared to solvers for most of the datasets. Thus, deflation-based solver is a much better alternative to the other solvers. Also, in this paper, we saw that since bundle adjustment problems tend to be very badly conditioned, explicit deflation can help in reducing the effective condition number, thus helping to speed up convergence of iterative methods. Here are some of the resources that we used for this work. Thank you.